It's a paper from the University of Maryland and Booz Allen Hamilton and the LPS labs. The first author is Edward Raff. He's done some other amazing work after this paper afterwards. And the other co-authors are Jared Sylvester and Robert Brandon. The paper is titled Malware Detection by Eating a Whole Executable. I'm going to put this on full screen now. And as you can see, I'm using their own slides for this presentation. Of course, if you find the slides created by authors for your own papers, you're more than welcome to use those slides in your own presentation as well. So, why are we talking about malware detection? What's the point of exploring other solutions of malware detection? Don't antivirus software suits already do this? Well, first of all, the malware detection problem is a very, very crucial and important issue, and it's becoming growingly paramount in terms of the risks involved. A single incident of malware infection can now cause millions in damages. The author point to examples such as WannaCry and Petya. Back then, I believe NotPetya had not been discovered yet, which had severe impact and incurred severe damages on a lot of different institutions and infrastructure. And they also mentioned that lives can be on the line. If a hospital infrastructure, if the IT infrastructure of a hospital gets infected, these authors had not encountered a similar scenario, but we did in the year 2018. Lives can be on the line. There can be actual lives in danger if there's a malware infection now. This is especially true in the domain of malware infecting or targeting control systems like SCADAs, as we had witnessed in the case of Stuxnet. But it's important to note that most antivirus products are built around a signature-based approach. So they're essentially using extended regular expressions and string matching to detect different types of malware or detect whether a particular binary is malware or not. This makes the approach reactionary. So we first have to, if we follow this approach, we first have to wait for a malware to come out, then extract a signature for that piece of malware, and then react to other infections of that malware. And this approach comes with another very critical downside or disadvantage. Signatures are very specific. They do not generalize. So you can use a signature for WannaCry to detect Petya, which is a problem in detecting novel malware. So malware detection sounds like a standard classification problem. We've already talked about how we can use machine learning and machine learning classifiers to detect malware. The authors specifically point out the success in using deep learning in various domains, such as object detection in images, image classification using convolutional neural networks, speech recognition in instances such as Alexa and Siri, and natural language processing, for example, sentiment analysis. What is the sentiment behind a particular sentence or a piece of text? Is it happy? Is it sad? And so on. However, the author points out that malware is more challenging for several reasons, which we're going to cover now. First of all, if you're considering a convolutional neural network-based approach, we have to consider the fact that binaries are not very spatially consistent. So convolutional neural networks assume that neighboring pixel values or neighboring pixels have some spatial correlation to each other. They provide some context of what's going on. However, in binaries, operations such as jumps and calls, which is like jumping to another piece of the code or calling a different function in the code, breaks this spatial consistency. And also, along the same lines, the spatial correlation ends at function boundaries, which means that if you're just looking at the code, the few lines of code that are within the same function define the boundaries of a spatial correlation, but the function can actually call another function from within the code, within the code block dedicated to that function, or there may be jump statements within the same function, and that breaks the spatial consistency and spatial correlation. There are, of course, multiple hierarchies of relationships in binary code. We can look at basic block level code. We can look at function level code. We can look at function composition into classes, and we can even go higher. This is a problem when we want to do feature engineering and feature extraction. Which level of abstraction, which level of relationships should we consider when we want to extract features for malware classification? Also, the authors note that malware complicates everything. They note that malware may intentionally break rules and format specifications. So we can't assume that malware binaries follow the same rules and format specifications that we expect. For example, there can be a bug in the code, which is by definition out of the specifications or rules of the development process, but that bug is an essential part of an exploit that the malware uses. Also, malware may intentionally try to obfuscate itself by changing its purpose, its apparent purpose, by changing signs of attribution, or by changing hints on what the binary does, especially the fact that it's even a malware. Also, if you're considering the x86 architecture, the x86 code gives you the freedom to make your programs, but it also gives malware the freedom to be weird. So we can have binaries with no code, just header. There can be binaries with only code, no header structure or no header information, no metadata available. There can be binaries encapsulated within binaries. There can be binaries composed of only the move instruction defined within the x86 framework. There can also be binaries that can detect if they are within a VM, a virtual machine. These instances and many more make the task of feature engineering for malware binaries very, very difficult. So the authors expand more on this complication in feature extraction. They note that simple things like getting values from the PE header, what we have already done in our malware detection module, can be non-trivial. They say that they've tested multiple libraries which disagree on the header content, which means that the specifications of the PE format and the PE header format are not strictly followed and are not strictly abided by. They note that even Windows does not strictly follow the PE specifications. So making this assumption that the PE header is always going to have the same structure and the same content of specifications is not necessarily true. They actually know that in many cases it turns out not to be true. They note that a number of companies have followed through on this domain knowledge-based path. They call this domain knowledge-based because this approach is particularly based on the assumption that the PE header specifications and structure is followed by Windows executables. They note that companies have developed multiple expensive feature extraction systems to reverse engineer the Windows loader, to hook deep into the OS, and to do enhanced emulated execution for dynamic analysis, which in the end translates into a huge amount of effort required from experts doing malware analysis and feature extraction. But note that this domain knowledge-based path is assuming a very restricted domain, and that's the domain of PE files. What if we want to come up with a model that works for any format, not just PE files, but any new format, like even PDFs or RTF files containing raw text? So the authors propose a domain knowledge-free approach. They define domain knowledge-free or DK-free from now on as an approach that does not encode any knowledge about the file format in the solution. It's just looking at the raw bytes. Of course, this implies that what they are going to do is based on a static analysis, not dynamic analysis, since they're just looking at the raw bytes and not the execution time, behavior, and performance of binaries. DK-free, in their opinion, also means that we can adapt to new file formats given the data, which means that they can build new models for PDFs, RTFs, and other file formats as they become a problem. And the model or the approach will be ready to work for any new file format as it arises, which can save time on feature extraction, resulting in a reduced time to solution factor. DK-free, domain knowledge free, also means that we can get rid of old problems, but also introduce new ones. This is essentially what they are trying to tackle in this work. And they propose a neural network-based solution as a potential candidate for a successful DK-free, domain knowledge-free approach. Why do they propose a neural network approach? Because so far, deep learning, deep neural networks have proven to be very efficient in doing automatic feature extraction and feature learning. So in image classification, what we pass to a convolutional neural network is just the pixel values. We don't do any manual feature engineering. The important features, the significant features, are learned by the CNN model itself. The same holds true for other types of deep learning models. They think that if they use a neural network approach, they may be able to reduce the feature engineering workload and essentially pass it on as one of the responsibilities, one of the things that the model itself needs to take care of during training. But how do we make a neural network process a whole binary? There are a number of problems in this task. Binaries are variable length. They can have variable sizes. Binaries are very large compared to other types of data typically processed by deep neural networks, and binaries can store many things. So the context, the semantics of binaries does not remain the same. There can be different modalities there. A piece of binary can be an operation, or it can also refer to a piece of data in an image used in the binary. The authors found that many best practices in the image classification domain do not translate to this particular space. So one of the major problems these guys have dealt with or had to deal with was the hardware limitations. Because the memory and the processing power in their testbed, which was an NVIDIA DGX1 box, was limited, they needed to make their network shallow instead of deep. This means they needed to come up with an architecture with only a few layers instead of many, many different layers. They also note that they needed to use large filter sizes for convolution operators instead of small ones to save memory and computation time. And they also needed to be very careful in how they handle the variable length of binaries. They note the memory constraints as the primary bottleneck. Modern frameworks, and remember this paper was written in late 2017, early 2018. Modern frameworks at that time were not designed for inputs of 2 million time steps. What do they mean by 2 million time steps? They are assuming that each byte in a 2 megabyte binary file is a time step, or is a piece of information that needs to be encoded in the feature vector. And they note that just the first convolution in a CNN-based approach to malware classification uses more than 40 gigabytes of RAM for backpropagation during training. They propose an architecture of this form. They begin with an input of the type byte string. So they just look at the byte string of malware samples. There's something in the chat box. Unfortunately, I can't see it. Can somebody tell me what's going on in the chat box? Joshua, can you tell me what the message in the chat box is?
It was just a little comment saying that my system can do that in less than an hour because I've got it doing protein folding on COVID-19 doing that.
You'd be surprised. We'll talk about this at the end, but that's an interesting comment. So they start with a byte string. They assume that it will be a typical malware binary or a benign binary will be around 1 to 2 megabytes in size. They actually cap the size of the input byte string to 2 megabytes. Then they do tokenization, which is what we've already done in our malware classification exercises. They convert these binaries into integers between 0 and 265 or 255. And then here is where the training begins. This is an embedding layer. And embedding, as you should already know, is essentially a compressed representation of the input data. This embedding layer is trained. So it trains, during training, this layer finds weights for each of these models, for each of these components, so that they can translate this very, very large tokenization input into a smaller smaller feature representation. And then they pass it to a gated convolutional network. They use a one-dimensional convolution with a kernel size of 500, which is really large compared to typical convolutional networks. with a Strida 500 with 128 filters, you're probably not familiar with gated convolutional networks. What this does is essentially it produces two sets of output. One is this value A, another is this value B. So it learns two sets of weights for the same input, as well as this sigma factor, and then it passes it to gating. This is essentially to deal with the large number of elements in the sequence. They're trying to handle large sequences using this approach. Then they pass it to a temporal max pooling layer. It just chooses the maximum and then passes it to a typical 128 dimensional forward layer, feed forward layer. And then in the end, they use a softmax layer, which determines whether the input is a malware or benign. So how do they evaluate this architecture? First, let's talk about the datasets they use. They use two groups of datasets, two different datasets. They call it dataset A and dataset B. The idea is to get a better estimate of, better evaluation of the generalization achieved by the model. Dataset B is comprised of many, many samples, I believe around 2 million samples of malware and benign binaries provided by their partner, which happens to be an antivirus company. And dataset A is public data, similar to the datasets we've used in the malware detection module. The benign samples come from Microsoft Windows, so they're just Microsoft Windows executables that are assumed to be benign. And the PE binaries come from public datasets. It's important to note that group B is trained on real-world samples of benign and malicious binaries. So now that they have the data and the model, they want to look at the results to measure, to answer these three questions. The first one is, how accurate is this malconf architecture? Is it better than what we could do before? They want to see whether malconf, what it is that this model learns. Does it learn more than what prior results did? And they want to essentially itemize what they have learned during this project. They note that a lot of common machine learning practices do not easily transfer to this domain, and they want to teach us what they have done to make this transfer possible. Now, here's the first set of results. You can see a comparison between the malconf model trained on 400,000 binaries coming from group B with the byte n-grams model. You've already trained an n-gram-based model in your malware classification module. And there is also another model that they use for comparison. It's a previously published benchmark based on applying deep learning to do malware classification based on PE header features only. Now you can see that the results, at least at the face of it, don't seem to be very impressive. So the best accuracy among these models for the group A is obtained by the PE header network. For group B, the best accuracy is obtained by the byte n-grams model. However, note that the difference between the accuracy of group A and group B for malconf is smaller than the similar difference for byte n-grams model and the PE header model. And they note that this can be a sign of enhanced robustness. So they say that the model is performing really well on group B and is performing similarly well on group A, which means that it generalizes pretty well. The other metric they report here is AUC, area under the curve. This metric is essentially a measure of how well does a model distinguish between the two classes. If we give it a malware sample, how many of the output probabilities are significantly higher than 50%. The higher it is, the more trustworthy, the more reliable the model becomes. And you can see that the highest AUC value belongs to malconf when tested on group A. Now, when they train on the larger corpus of 2 million binaries, instead of 400,000 binaries, now they train on 2 million binaries. They increase the size of the data set. First of all, they note that it took them about a month to train it on a DGX1 server. DGX1 used to be a very powerful server used for educational institutions. And the Ngrams model took about a month to count using 12 parallel servers working at the same time. You can see that the accuracy for group A under malconf is the best, around 94%. However, byte ngram models do best for group B. A very important finding in the author's opinion is that the AUC factor is really, really high for the malconf model compared to the ngrams model, which means that when it detects something as malware or benign, it has the result is a lot more reliable. It has a lot more confidence than the ngrams model. And it also shows that malconf still has growth on the learning curve. So the more samples you feed it, it learns better. The accuracy increases. But the ngrams model overfits. So you can see that a model trained on group B does not do very well on group A. And by that, I mean an ngrams model does not do well on group A. So it doesn't generalize very well to unseen samples. However, malconf has a better generalization between these two groups. Now, what is malconf learning? The prior work of these authors has reported that byte ngrams, the models based on byte ngrams, really only learn the PE header. Similarly, they expect that the PE header to make a big portion of any model because it's easiest to learn. It's very structured and it contains a lot of useful information regarding the nature of binaries. However, since malconf has temporal max pooling, we can also look back and see which areas of the binaries were more emphasized on using the trained model. And also they mention that using tools to parse the PE header, they can look at what sections the important blocks were found in. So here's how they represent their findings. In an experiment with 26,000 malicious samples and 19,000 benign samples, you can see that the most important blocks for detecting malicious samples were found under the PE header. The same happens for the benign samples. You can see that the detection, the model has used bytes or blocks found under text or data or R data in different samples as well. A very interesting finding that the authors also note too is this UPX1 piece of the binary, which essentially refers to the use of the UPX packer. Remember, a packer is a software that compresses binaries into a more compressed format, which are decompressed during runtime. So one thing they note that is a lot of the current state of the art see the use of UPX as a sign of the piece of binary being malware. However, non-malware binaries may have also used UPX as a packer. So UPX can be a misleading feature, and they claim that these numbers show that Malconf is not putting that much importance on this particular feature. And they also note that Malcolm makes significant use of resource and code sections, which is a strong indication that they are learning to extract far more information than previous approaches, which mostly focus only on PE headers and some other parts, such as the type of packer used. They also note that they could not use batch normalization in this work. And why is that? They note it's mostly because, probably because they do not provide a more in-depth analysis, is probably because of the different modalities in the binary data, which makes normalization, which essentially means bringing the distribution of data under a normal distribution curve, meaningless, because the data are coming from different distributions and you can't just batch them, you can't just put them all under the same normal curve. This is not in the slides, but it's interesting to know that they use a type of regularization that penalizes the correlation between convolutional layers just before the output layer, which is proved to be very efficient in this case. So this was the gist of their work. I highly recommend that you all get to read this paper as well. This is actually required as part of the learning components of the deep learning module. Now, let us have, I'm going to give 10 minutes for questions or comments or general discussion on this paper. Does anybody want to share a comment or pose a question? Nancy?
I wanted to know the last sentence or last few sentences you just said, that they were using a normalizer on the layer before the output layer. Was that a regularizer or was that an actual normalizing
No, it's not a normalization technique. It's a regularization technique. Remember, this is just to refresh the memory of everyone in the class. Regularization refers to techniques used to mitigate overfitting, right? So when you go through the deep learning module, you'll learn about dropout as a regularization technique. That regularization approach is different from batch normalization, which normalizes the input to reduce the computational loads. Now, does anybody think that there is something missing in this paper or in this approach? I have a few thoughts, but I'm going to wait for you guys to share your thoughts first before I bias them. Sai?
Hello, can you hear me?
Yes.
Awesome. So I know you said this was from 2017, and just from working with machine learning antivirus platforms, I'm curious if this was really just trying to take a file of some sort that's already in an environment rather than discovering something when it enters an environment.
Well, they are essentially proposing a static analysis approach, which means that it's independent of the environment. They have the binary file, they have access to the raw binary, and they want to figure out whether that binary is malware or benign.
Okay.
All right. Any other thoughts? So what do you think about the 2 megabyte cap on the size of the binaries these guys are looking at? What happens if a binary is larger than 2 megabytes? Any thoughts on that? So Sai is saying that it would be cut off. Essentially, yes, they're just looking at the first 2 megabytes and they're discarding the remaining bytes. Do you think that this approach is useful in the real world settings? Nancy is asking, are malwares normally that big? They can be. Joshua?
Yeah, as far as being useful, I'd say it is useful, but I think that because my paper was also on Ember, which I'm sure you're familiar with, and although Ember and Malcolm are two different, Malcolm's feature lists, what I say is I think that it is useful, but it should be compared to more traditional or I'm sorry, benchmark like accepted models that have already been published to get like a real estimate of its performance, which I noticed it had two models that it was compared to in your slides, but I'm assuming those were just generic, like the bytegram models.
One is based on n-gram models of the bytes. The other is based on a deep neural network trained on the information available in PE headers. But Joshua makes a very good point. Their comparison is not comprehensive. There are many, many other malware classification models that they could have compared the performance of Malcolm's to, and they did not. Now, another interesting thing to note here is the performance of Malcolm is not actually too far from the performance of the n-gram model, bytes n-gram model. And the bytes n-gram model is cheaper to train because you don't necessarily need to use a GPU server to train it. You can just parallelize it over multiple servers and apply a decision tree model or other types of ensemble architectures to train it. It will make it even cheaper to use at runtime. Why do you think there's an advantage in using such a complex model, I'm referring to Malcolm, to achieve those few percentages of enhanced accuracy? Any thoughts on that? So Nancy is mentioning scalability, and Sai is pointing to the potential for reduced false positive rates. Yes, the paper is essentially noting this reduction in false positive rates in different terms. remember the AUC metric? The AUC metric is telling us how confident the model is in performing the classification task. The more confident it is, the lower the chance of false positives becomes, essentially. And that can help with reducing man hours in dealing with the malware, both be it in further analysis or just looking at it from a security engineer's point of view. Nance's point on the scalability is interesting. So the authors explicitly mentioned that their model is very difficult to train using parallel or distributed architectures. They try to make it more scalable, but it's still not as scalable as simpler models such as the byte n-grams model. The main selling point of this approach, in my opinion, is twofold. The first one is the fact that they don't do any manual feature engineering. They just pass the raw bytes to the model and the features are learned automatically through the training process. This is in contrast with the n-grams approach. N-grams is essentially a way to produce features, a way to extract features, right? How do we know which n is best? We have to try multiple approaches. And how do we know that the n-gram approach is the best approach for feature extraction? We have to compare it with other approaches for feature extraction to figure this out. Another selling point is the high AUC values, which refers to a higher confidence after training in detecting in distinguishing between malware and benign samples. Okay, any other thoughts? So there are two other things that I want to point out here. One is in their test bed and test methodology. Sai asks if this has been tested again with more modern technology. Yes, first of all, more recent publications in later 2018 and 2019 have actually compared the performance of newer models, more recent models with Malconf as a benchmark. And also you will be training Malconf on Ember as part of your assignment, as part of your midterm project. So you will perform this test on your own. Now, note that in the test, in the experimental validation of Malconf, they only look at PE binaries. So there's no way that they can check to see whether their model can apply to different types, different file formats or not. They don't know whether they can detect malware in PDF files or not. It may be successful in detecting PDF malwares as well. And just to note, there are actual PDF malwares, but they do not present any results on that. The other thing to note is that their input vector is too large and it doesn't make efficient use of the sequential structure in the input. Even though they mention a temporal view or a temporal approach to the sequence, there are a lot of sequential aspects that they are missing out using this convolutional based approach. So maybe using an LSTM model could help. The paper explicitly talks about different RNN-based, recurrent neural network-based approaches and architectures and the downsides associated with those approaches, but the study of different architectures as presented in the paper is lacking. It's not complete. And newer architectures more recent proposals for malware classification actually talk about or present RNN-based architectures that perform better and can be trained in less time with lower computation cost. All right, so let us finish our discussion on this paper and move on to the next presentation. I believe Nancy is next. Is that right? Nancy?
I'm listed as third, but if the second person going is not doing it, then I guess I am.
Yes, so the second presentation is going to be rescheduled for the 15th. So let me first stop this recording for now.